Hello, this is a lecture for Chapter 5, Block Diagram. This is part 1. Um, the Chapter 5 is about system models. So it has three topics, and the first one is transfer function, and the second one is the block diagram, and the third one is the state variable models. So we're only going to talk about block diagram for this chapter and a little bit of MATLAB at the end. So the block diagrams, it's entirely in S domain, consists of blocks and lines and a summation node. Okay, just those three elements. So you have a lines, a signals. It could be input signal or the output signals. So those like X in the first picture. Okay, so that's a signal. Yeah, this is a signal. Okay, and the transfer functions are inside the blocks. So whenever the signal goes through the block, you multiply. So in the second picture, the figure 5.1.1b, um, another way to write that algebraically is f times t equals x. Okay? So whenever you go through the block, you multiply. Okay? And if you want to sum or subtract, if you want to add or subtract two signals, you use a circle. Sometimes in other books you might see circle with the x. The same thing with the plus and minus. So you have an x and y. This means you add x, but you subtract y. So x minus y equals z. Okay. And signal can split. Okay. So signal can split. It's not, you can't add them together without a circle, but the signal can split. So the last picture shows a signal, how the signal can go into two different directions. So there are three basic blocks. The first one is a multiplier. So whenever the signal goes through the block, you multiply by a constant number. So in the first picture, figure 1.5.1.2a, it says f of s times a constant number k equals capital X. Okay, and then b, you have a differentiator. Okay, so that is this one. If I rewrite this in algebraically, you have f of s times, f of s times 1 over s equals x of s. So what are you doing to f of s to get x of s? When you multiply by s on both sides, you have s times x of s, and then take an inverse or plus transform. Okay, and you'll find this is got the f of t equals derivative of x with respect to time. And then by solving for x of t, you have an integral of f of t dt. What does that mean? What are you doing to f? Okay, what happens to f after it goes through the block that's block of 1 over s? You integrate it. So you should just get used to it. Whenever you see a block that has 1 over s, it's an integrator. Okay. So there's one another type of block which is also important, is a differentiator. Okay? Differentiator will have, can you guess what the differentiator will look like? So this is figure C, so I made up my figure. And if you have a signal that's going in, okay, you can just name it however you want. Let's say you have an x of s that's going in. I want to differentiate it. Okay, I want to differentiate it to get, let's say, y of s. Okay, then the block should be s. Why? Let's see. X of s times s equals y of s. In time domain, this is dx over dt equals y of t. So what happened to x? You differentiated it. Okay, as it goes through this block of s, you differentiate the signal. So now, how to represent a differential equation? Let's say you have a differential equation, x dot plus 7x equals f of t. Okay, how do you represent it? Many different ways. So what you could do, is just take a Laplace transform right away. Okay, take a Laplace transform right away. You have where am I? Okay, hang on. Hang on. I meant all the way from here. Okay, so take a Laplace transform. So you have s times capital X of s plus 7 times x of s equals f of s. Okay, then x of s equals f of s times 1 over s plus 7. Okay, and then you can express it as a block diagram as you put in f of s and you multiply by 1 over s plus 7 and you get an output of x of s. Okay, the reason I didn't write this as, okay, this is the correct expression. The reason why I didn't write this as x of s and s plus 7 and you have f of s, so this is not correct. Okay, why is that? Because when you have a differential equation, usually what's given? Your given is f of t. So this is your given input. Okay, this is your given input to the system, and your goal is usually what? Solve for x of t. Okay, so what's coming out should be the output x of t. Yeah, so I'm going to just erase that expression. So another way to write it is, there are many ways to write this. Okay, this is just another way. So what you do is you solve for x dot in the original equation. So you have x dot equals f of t minus 7x. So what you do is you line up. Okay, you have a signal that's called the x of s, and then you put in an integrator. Okay, so what should be the signal before you integrate? You have a signal, and then if after you integrate, you get x of s. What would that be? This is the x dot, okay, in time domain, okay? So in the estimate, this is x times x of s, okay? That's the name for the signal. This is the x dot, okay? So now, what does the second equation say? This equation says x dot is a summation of two things, okay? Two things. One of them is f of s plus, and then you have to subtract 7. So multiply 7 times x before you fit it to the circle, okay, before you add them together, okay, and then this should be negative, okay. So this is the picture in B. Okay? So sometimes the reason why we use the second option, second type of block diagram, is because it gives us more detail about the problem, okay, detail about the system. So I'm gonna erase the redundant picture. Yeah, so this is just the expression of the second equation right there. Okay. Okay, so now next. Some simplification can be made, okay, by just looking at it. Just instantly you might be able to recognize it. When you go to controls, you have to be that good. You have to be able to look at it and recognize, okay, how to simplify it. So for now, just never mind. Okay, never mind all this. So just look at a signal that's going in, that's your input, R sub s. Okay, and then you have signal that's coming out, that's called a C sub s. Okay, just never mind what it says up there. Okay, C sub s, and this is R sub s. Okay, so now after every time you go through a block, what happens? You multiply. Okay, so I much rather not name them. Okay, I don't want to name these signals with the new names. Okay, except for the input and the output. The only thing that's deserving a name is input and output. Okay, any intermediate signals, I don't want to call it x1, x2. Okay, I just got rid of those. So this line is g1 times r sub s. And then what do? You continuously multiply. Okay, you multiply g2, and you multiply g3. So in the end, what did you do? Going from r to c, what did you do? You multiply by r, g1 times g2 times g3. So you can just make it into one block with a G1, G2, and G3. Okay, amazingly, in MATLAB, you can use what's called a series command. Yeah, G1 and G2 will multiply G1 times G2 for you. Okay, so let's see. So this is a MATLAB command. MATLAB. Okay. So it might be useful when you go to controls. So now another types of blocks that you should just recognize instantly is the parallel blocks. So you have a signal that splits, okay? That split. You're going to three different places, okay? So this is R, this is R, this is R. All of them are on the left hand side. And after you go through these blocks, you have R times G1 for the first one, okay? And you have R times G2, R times G3. And then when you sum them up together, okay, when you sum them up together, so let's just use plus for now, okay? Plus, okay? You'll have C sub S equals R times G1 plus R times G2 plus R times G3. That is, you can just take out R, factor R out. You'll have G1 plus G2 plus G3 times R. Okay? So these techniques are very useful in recognizing, like simplifying the block diagrams. So here it is. So you have one block, okay? One block with a G1 plus G2 plus G3. So another type of block that you have to recognize is what's called a negative feedback loop. Okay? So this structure occurs so many times, so often, once you look at it, you say, oh, that's negative feedback loop. So let's start from whenever the feedback occurs. Okay, so you have a signal X that's going out, so that's your only output of the system. And you have only input of the system is F sub S. What is G and H? They're transfer functions. Okay, they're not signals. So this is X, that means this is also X. Okay, and you multiply, so you get H times X. Yeah, and this one, it will be F minus H times X. And you multiply by G, you have G times F minus H times X. Okay, so what does that mean? Whenever you label a line twice, whenever you give a line, a signal, two different names, you have an equation to solve. So you have a G times F minus H X is also called X. Okay? One thing to note is that you don't just keep going round and round and round multiple times. Okay? Once you reach the line that you've been there before, you stop. So now let's multiply, distribute. Okay? And keep in mind you're solving for the output. You're always solving for the output. So you have an X times 1 plus GH equals G times F. So you have to be able to distinguish what's output, what's an input. Okay, input. There we go. There we go. That's an input. And every single term should have either input or output. Okay? This one has F. The second one has X. The last one is X. Okay? Every single term should have either input or output. Okay? Never both. Okay? Never both or neither. So now your output equals G divided by 1 plus GH times F. So what's your transfer function? X divided by F equals G over 1 plus GH, which can be drawn this way. Okay? So remember, whenever you see this configuration, something times the transfer function equals output. This always, you should just recognize this is X divided by F equals that block G divided by 1 plus GH. Yeah, that makes sense, right? Because this one says F times the transfer function G over 1 plus GH equals X. So divide the both sides by F, you get X over F. So when I see this type of block, I just recognize right away. Okay, that's X over F. Output over input equals that transfer function right there. So block diagram of a system using constant gain and the integrators only. Okay, so this problem, I think this was an example problem. Draw a block diagram that corresponds to this. How does it work? What you do is you solve for the highest order term. X double dot equals negative 7x dot minus 10x plus f's of t. Okay, f's of t. Then what you do is your output is always x. Okay, and then you need two integrator to get to x. So whenever you integrate Okay, going backwards, you differentiate. So this is your x dot. This one will be your x double dot. Okay, this one, um, I don't really have to label them. Okay, I'm just labeling them for your convenience. So everything is in S domain, but it's not a crime to just call it. Oh, this is a derivative of x in the time domain. Okay, so now we have x and x dot and x double dot lined up. Okay, so now you're gonna start writing the sum. X double dot is equal to the summation of f. Okay, plus, and then you have minus 10 times x. So I'll multiply by 10 times x. I'll subtract. Okay, subtract. And is it clear what to do with the negative 7x dot? Where is x dot? X dot is right here. Okay, right here. And you multiply by 7. Okay, and subtract. Okay, so that's one representation of the block. One block diagram. I mean, it's one of many block diagram representation for that system. So let me get rid of redundant picture. It's right there. Did you notice it's just right there? So let me just write in. This is x dot in time domain. This is x double dot in time domain, or it's s squared times x of s. Okay. And here, so this is x. This is 10 times x. Okay. So let's see. So this is definitely true. There can be more than one correct diagram. Okay, I used to always wonder about why I have to write that particular block diagram, because I was thinking, you can't really complain if I decide to go f of s, x of s. Okay, I know the transfer function 1 over s squared plus 7s plus 10. What's wrong with this? Nothing. Okay, nothing. Okay, that's absolutely correct too. So transfer function from a block diagram. Let's see. The inputs of the system there's actually only one input. That's your f of s. The output of the system. Oh, wait a minute. I think I made a mistake. Can you tell which one? Okay. I should really read what I wrote. Look. Oops. I didn't mean that. Okay. Look, I have another input. Okay. I didn't say that one. So you have g sub s. Okay, g sub s. Okay. So since you have two inputs and one output, two transfer functions are possible. Y input number, only input of the system divided by the input number. I'm sorry, only output of the system divided by the input number 1, f, or the only output y divided by the input number 2, g sub s. So transfer function, how would you find it? I tend to do this type of problem just using algebra. There are other ways to do it by recognizing those serial blocks, parallel blocks, and negative feedback system. But now I do it differently. Okay, so when you go to a control class, I don't want you to tell your control teacher, oh, this is how Dr. Han taught us. Just keep in mind that whatever I teach you is it's an alternative to what you will be learning in your actual controls class. So let's see. What I like to do is massive algebra. Okay, so this is y, so this is y, so this is 5y. Okay, really only thing that are worth named are the inputs and outputs and the transfer functions. Okay, I don't like to name the signal. Here I see x of s. I usually like to just cross that out. Can I use black? Is it too bold? Maybe just get rid of that. Okay, I don't want to see that. So going back to blue, here it is. Okay, so this is y, this is y, this is 3y. So now this line right here is f minus 3y. That's it, right? Then now you multiply 1 over s, f minus 3y. Here it is. Now you multiply 4. Why didn't I just multiply 4 divided by s from the beginning? Okay, 4 divided by s times f minus 3y. Okay, now this line, it's coming out of, we have 3 signals going in. Okay, so this will be g plus 4 over s times f minus 3y minus 5y. Okay, So now continue. Okay, now continue. So now multiply by, okay, this is worth writing outside. You have g plus 4 divided by s, f minus 3y. I'm copying everything down. Okay, multiply by the last block, 1 over s, that's y. Right? That's the only time, that's the first time that it happened that you're naming a line, a signal, by two different names. Okay? And what did I tell you? Every single term should have either input or output. Okay? So if you multiply everything out, you'll be able to tell. Let's multiply. Okay? Let's distribute. You have 1 over s times g plus, next one is 4 divided by s squared f minus 12 divided by s squared y. Ooh, I'm distributing. Okay. 5 over s times y equals y. Every single term, what did I say? Okay. Either has an input or output. Okay. Input or output. You see? It's supposed to be an eraser. Okay. Oh, goodness. I didn't mean that. Now I can't remember what that was. I don't think that's it. Okay. Okay, so that was minus 5 over s. Here, I'm trying to highlight the inputs and outputs. Here we go. Okay, so now what do you have to do in your next step? What's your next step? You solve for y. So you collect all the y's. You have y 1 plus 5 over s plus 12 over s squared equals, leave everything on the other side. You have 1 over s g plus 4 over s squared f. So now y is, output is, okay, 1 over s divided by 1 plus 5 over s plus 12 over s squared times g plus 4 over s squared divided by 1 plus 5 over s plus 12 over s squared f. Okay, so now I really cannot help myself because I really want to simplify. Y equals, I multiply top and bottom by s squared, so you'll have s, okay, s squared plus 5s plus 12 g plus 4 divided by same denominator f. Okay, so when I get desperate, I drop all the function of s. Okay, they're all functions of s, right? Y is a function of x, g is a function of s, f is a function of s. Now I'm ready for my transfer function. So what's a transfer function? Transfer function y over f, okay, is what? Is the ratio of y to f while all the other inputs been turned off. Okay? So what's the other input? There's only one other input, which is g. Okay, turn that off by setting that equal to 0, setting this equal to 0. Okay, now y over f is just simply this term, 4 divided by s squared plus 5s plus 12. That's your transfer function, y over f. Similarly, transfer function y over g. Okay, now s is coming back, okay, because I'm not so desperate anymore. So s divided by s squared plus 5s plus 12. That's your other transfer function. So that's how I find the transfer function. Okay, but that's not, this is not actually typical. Okay, so control people will look at this and say, oh, I see a negative feedback system right here. I'm going to use, which color should I use? Cosmic. Here we go, cosmic color. Okay, here we go, cosmic color. Okay, so people will recognize, oh, that's a negative feedback system. Okay, we do have a formula for that, right? G divided by 1 plus GH. And then, oh, look, we have 2 blocks, the serial blocks. You just multiply those two together, okay? And after that, okay, if you're trying to find y over f, you set g equal to 0 temporarily, and you see the whole picture looks like another negative feedback system, okay? So that's how they simplify, and then you'll learn that more when you actually go to control class, okay? So here it is. This is another example that I prepared for this class. So would you like to try? It's always the feedback loop that's a problem. Okay, the loop, whenever you feed the signal forward, it's not that difficult. Whenever you see a line that's coming out of the middle ish, okay, and going back to the left, that usually give lots of problem. So let's try. Yeah. So now that's your output and two inputs. Here it is. Should I have changed the colors like this? Will that do? Ooh, it became green. There we go. Okay. So now let's see. This is x. That means this is x. This is 4 times x. Okay. And then this one has got a problem because this is g plus 4x minus what? Minus 5 times what? I don't know what that is. Okay. So here it's got a temporary name of y sub s. Okay. Y sub s doesn't mean anything. Okay. Really, the only variable you should pay attention to is your input and output and transfer functions. Intermediate, the signals that's marked right in the middle of the block diagram. What is y, right? What is y? So I usually just get rid of it, okay? But I do need a temporary name for that line, that signal. So what I'm gonna do is instead of using y, I'm gonna use star, okay? The reason why I'm using star, you can use y, okay? The reason why I'm using star is to let you know, let me, okay? So I can remember it's a temporary variable that needs to disappear, okay? So this is 5 times star. And then here, now finally, this is g plus 4x minus 5 times star. Okay, continue. Okay, continue. And this line right there, g plus 4x minus 5 star times 1 over s equals star again. Okay, so now we have an equation. Why? Because the same line, same signal was named twice. Okay, so now solve for the s. So I'll just multiply by s on both sides. Why? Because I don't want to have fraction. So you have g plus 4x minus 5 times star is s times star. So what's star? Then that's g plus 4x divided by s plus 5. Okay? You need to save this information. Okay? So now I can actually move forward from the signal. So this is equal to 3 times that. Okay? 3 times this star, okay, but star is no longer unknown. Okay, you're gonna if I have more space, I'll just write this whole expression there. Okay, then here this is f minus 3 times star. This is f minus 3 times star times 1 over s. Okay, and then now we have an equation. Why? Because this line is on that line that has a name, official name of output of x of s. So I have an equation right here. F minus 3 times star. I think now is the time to write down what that is exactly. Yeah, multiply by 1 over s. What did I just do? I just rewrote it. Okay, equals x. So I'm going to use the same trick of multiplying by the common denominator, which is s times s plus 5 on both sides. Okay, don't forget to distribute, by the way. So once you do that, you'll have right hand side s times s plus 5 times x, but on the left hand side, you will have f times s plus 5. Do you agree? Okay, minus 3 times g plus 4x. Okay, you have to distribute this whole thing, each term, right? Okay. So next, take a highlighter. Get a highlighter. So my inputs are G and F. Where's my G and F? Yeah, and my outputs are only one output. My output is X and X. Okay, so now you're gonna collect terms. So what's the coefficient of X? You have S squared plus 5S that I got from here on the right hand side, and then you have moved that one over. You have a plus 12. Okay, equals on the other side, I have s plus 5 times f and I have minus 3 times g. Okay, I think I did everything correctly. So you have x divided by f, the transfer function. Let's not forget. Okay, I'm skipping one algebraic step. That is s plus 5 divided by s squared plus 5s plus 12. Okay, how did I get this? I divided both sides by the coefficient of x. And the transfer function, yeah, x over g equals -3 divided by s squared plus 5s plus 12. And that's the final answer. Those are your final answers. Okay? So your goal, whenever you have a block diagram, you're gonna find the transfer function of the output over input. So in fact, sometimes you might want to just have a block diagram because you can see the structure where the input comes in, okay, or where what happens to where is the sensor data coming in, okay. So whenever you have a feedback loop like this, okay, so that signifies there is a sensor, okay, there's a sensor. Yeah, you're actually making measurements. So, oh my, okay, so let's, I'm gonna actually start you off, I'm gonna just start you with this, for this problem. I might not finish, okay, I might just leave it up to you to finish the algebra. So this is 4 times x. The first thing to do is I think I'll get rid of all this, okay, get rid of all that, okay. So this is 4x, this is f minus 4x. This is 7 times f minus 4x. Okay, I'm naming all these signals. And then this one is 3 times x. So right now this will be 7 times f minus 4x minus 3x. And you multiply by 1 over s. Okay, so I'm going to take it out here. 7 times f minus 4x minus 3x minus 3x. All of that stuff multiply by 1 over s. And what do? You add it to g. Okay, then what do? After that, you multiply by 1 over s, you get a capital X. Now search for the input and output. You see x, g, f, and x right here. Okay, every single term should have either input or output. So what's your goal? You solve for x. Okay, so what's next? Ooh, there's another problem. And some MATLAB. Okay, so I actually want to show you one example problem. So this is an example problem where I use MATLAB. Okay, so I don't actually use MATLAB for this kind of what is it, the algebra. Okay, so MATLAB really wants numbers, right? Values. It doesn't usually want to do any algebra problems. So here I'm using a symbolic toolbox. So this looks really complicated. This is the example 5.2 of your future controls book. Okay, so they'll tell you to solve it different way. Okay, which I'll show you next. Okay, so instead of me doing the algebra, I decided to have a computer do the algebra. So what I realized was I pay attention to wherever the feedback occurs. Okay, so this is feedback. Here we go. So this is C. Okay. Okay, this has a name. Okay, no problem. Okay, this is not a feedback loop. Okay, this is actually going forward. Okay, don't worry about that one for now. What I'm worried about is that whenever you take a signal and feed it backward, I need a name for that. Okay, so I decided I'm actually gonna keep temporary name. Normally I would call this one star. I decided to keep their given name V3, okay, V3 of S, and I decided to get rid of all the other temporary names. Get rid of that one, get rid of that one, get rid of that one. I don't need any of that stuff, okay? You don't want us to solve a massive equation with so many equations. I'd rather not name any of those, okay? So here I look at it and I see a problem area. It's like right here, okay? Ooh, what is this? Oh, it's okay, cosmic color. It's right here. The problem area is like right there. I need a name for that one. Okay. So what I decided to do was, strange. I actually decided to use a V3. I could just use a V4, but I used the V3. Okay, no problem. Okay, so this is V3, and then this is temporary name. Okay, I have to get rid of it as soon as possible. And this line is G2 times V3. Okay, so now I'm ready to do this problem. So first, in MATLAB, I define all my inputs and outputs and the transfer functions as a symbolic variable. That's R, input, C, output, and all the transfer functions, G1, G2, and G3, and H2, and H1, H2, and H3. And one more, okay, one more, I'm using V3, okay? Why? Because I know that feedback has to occur at V4. I really should have actually used V4. I don't know why I used V3. So, it doesn't matter, okay? It doesn't matter. So now what I did was the first, my equation 1, okay, equation 1, it starts from R, okay? It starts from R, so I have R minus H1 times, see, this is so H1 times the name for that signal right there. So G2 times V3. Do you see that? Okay, you see this? This is this line right there. Okay. Yeah. So now I'll just change the color, and up to here, multiply by G1. That's right here. Okay, you'll multiply by G1. Yeah. Oh, what color can I use now? Orange. How about orange? Okay, and then what I did was this line right there, okay, is the purple one minus H2 times that V4, okay. Yeah, so up to here, okay, up to here, that's my orange line right there, okay. And what's that equal to? Because that line is already named as what? V3, okay. So I have an equation. So what do I do next? Instead of doing the algebra myself, I let MATLAB do it. I said solve equation 1. Oh, by the way, there's a 2 equal sign, so you're not really setting that equal to each. What do you call those equal signs? You're not assigning a value. Okay. I can't quite remember what it is. But anyway, so you solve for the equation 1 for V3. Okay, V3. So now I'm going to set that equal to V3. Now V3 is in terms of all the other variables. Okay, inputs and outputs and all the transfer functions. So now normally I call the star, but I can hardly use star for MATLAB. So for the equation 2 starts from V3. Okay, so you have V3, you multiply G2. That's that line right there. Okay, so maybe I can use a highlighter. How about the blue one? Okay, right there. Okay, so this is up to G2 times V3. Okay, then the next one, the pink. I'm going to use that pink right there. What is this? It's from here to here, I believe. Okay, so you have V3 times G2 plus V3 minus H3 times C. Okay, that one. So that's your pink signal. So now I only have to do one more thing. You multiply by G3 and you get C. Okay, so how long do you think it took me to type all this? Okay, not long. A minute maybe. Okay, it's just taking a long time to explain this. So now MATLAB this is really coming from Maple. These are really Maple commands. Maple. Okay, this is the computer program. So you simplify it. First, I solve the equation 2 for C, the output. Okay, then you collect terms so that you can factor R out. Okay, then I simplified it, and then right now this is so R is factored out. Oh, I didn't mean that. Okay, R is factored out. So what it says here, this is what C is equal to. Okay, this is what C is. So if you want to find what C over R, that's equal to G1 times G3 times G2 plus 1. Okay, what is this 1? Oh yeah, 1. Okay, divide by, do I have to write all that stuff? G3 H3 plus 1 times G2 H2 plus G1 G2 H1 plus 1. Follow that. Okay, there's a multiplication right there. So that's your transfer function. That's your answer. Okay. So I can beat you on any day. Okay. I mean, if I'm allowed to use Maple or MATLAB, okay? Because what they'll teach you in controls is series of a reduction, okay, technique, okay? So I'm just gonna briefly explain this. So I want blue, Okay, here it is. So this is what they do: solution via reduction, okay? So first, they kind of recognize, okay, recognize this. Oof, what can I erase? Can I just erase everything? Okay, just gonna get rid of everything. I still don't need the V1 and all that stuff. Okay. I'll just get rid of everything. Why not? Okay. So, what color can I use? Ooh, how about blue? No, that's green. Green. Okay. They recognize. Okay. This is a negative feedback loop. Okay. That has a formula where this G3 H3 can be replaced with a G3 divided by 1 plus G3 times H3. Okay. Remember that? That's a negative feedback loop. So that's what's shown right there. Okay. And then they realize, wait a minute, this is almost a negative feedback loop. Okay. What you need to do is you need to get this line out of the way first. Okay. So they move the line forward. Okay. Now they're going to take the signal out from here. Okay. Instead of there. Okay. In the process of doing that, you'll have to divide by G2. Okay. G2 and fit it to it. Okay. So that's the second step. Move the line from here to there. Okay. And then you have a 1 over G2. Why is that? Because originally when you used to take a signal from here, okay, oh, it's simply because it's your V4, okay, your V4 is equal to V3 times G2, okay. So before you used to take just a V3, which is V4 divided by G2, okay. Now since you're taking a signal V4, you have to divide by G2 to make it equal to V3, previous V3. So anyway, okay, so I'm not going to teach you this technique. I just wanted to tell you. So they do a series of reduction. Okay. So how many pictures do you think they have to draw? Many. Okay. Okay. Many. Because they actually did the two things in one picture. Do you think they're done? I think not. Look at this. This is the second picture. This is the third picture. Fourth, fifth, and sixth. Oh, okay. I much rather do algebra. Okay. So when you go to the controls class, ME3334, okay, you still have to learn this technique, okay, because really good people who are good at this, they recognize, they look at it right away, and then they can simplify in their head right away, okay, which can be a lot faster than my algebra. All right, so that's all I'm going to cover for block diagram, okay. You do not have to know how to simplify. Okay, you do not. Oh, okay, where am I? Okay, you do not need to know how to simplify using nice example 5.2, something like this. You do not need to do it. Can I just put a big X through it? Okay, just don't tell your control teacher. Okay, so for the block diagram, all you have to do, okay, is try example 5.2. I'm sorry, the problem 5.2 and 5.4. Okay, and I think it says block diagram reduction. Let's just scratch that out. Okay, just use algebra. Oh, what is this? Don't restart. Okay, and then problem 5.4. Yeah, that looks reasonable. Okay, so next topic I'll cover is ODE 45, and I'll do that in a different video. Okay, thank you.